Practice FRQ number 1. The first part of this FRQ is having us find the product rule, or finding the derivative of f times g, which would require us to use the product rule. So we know the product rule is f prime times g plus f times g prime. So what is f prime? I don't like looking at the square root of x like that. I like looking at it as 1 raised to the 1/2. That makes it easier for me to think about its derivative. Its derivative, if I went and took the derivative of that, would be 1/2 x raised to negative 1/2, because you have to take 1 away from the 1/2. And this would mean 1 over 2 square root of x. Okay, so the negative exponent makes the x go to the bottom of the fraction, and we get 1 over 2 square root of x. So we have 1 over 2 square root of x for f prime, and then we multiply it by g, which is just going to be x minus 1 to the second power. Then we go plus. Okay, then the next part, this part, we have the f times g prime. When I'm looking at g, I take the derivative of that, would be 2 times x minus 1 raised to the 1 power times the derivative of the inside, which is just 1. So we have a lot of extra stuff going on here if we do the chain rule. And the reason why chain rule doesn't matter much here is because the derivative of the inside is just 1. So when we simplify this even more, we get 2x minus 2. So we have 2x minus 2, and then that's it. There it is. That's your answer. Yes, you can simplify this, but since this is an FRQ, I'm just going to do the calculus stuff and then be done. I don't need to do any of the algebra stuff on an FRQ. All right, now let's look at the next one. The next one's a little bit more fun because we're doing a composition here. Now, usually with the composition, we're going to be doing a chain rule somehow, but this one has a little trick because f is a square root, and g is x minus 1 raised to the second power. Now, this does simplify. It simplifies to x minus 1, but not just x minus 1. It simplifies to the absolute value of x minus 1. Why? Why is that true? Well, let me show you why by using a graph. Let's start with the square root of x. When I do a graph, when I graph square root of x, we know that we can only plug in 0 in all positive numbers. So the positive side of the x-axis is the only side that gets a line. We cannot plug in negative numbers into the square root of x. Okay, but what happens when we have an x squared inside of the square root? Well, if we sit and think about x squared inside of a square root, we can actually now plug in negative numbers to this x. Think about that. Because we're able to plug in a negative 5, because there's a squared, that would be positive 25. Negative 5 times negative 5 would be positive 25. So now we could plug in all these negative numbers. And so we should be seeing something happening on this side of the x-axis, because now we're allowed to plug in negative numbers. So let's get rid of this guy while we're talking here. Now, you would think that when you're simplifying this, the x squared just cancels out with the square root, and so you just get left with x. And this is the graph you would get. This is the graph of x. However, this should not happen. Like, your result of a square root should never be negative. So when we think about that, when we plug in a negative, your result has to be a positive number, because all the results of a square root function is a positive number. So how would this side of the equation look if all of these y values down here are actually supposed to be positive? Yeah, can you see it? Yeah, do you see it? Do you see the absolute values? Let's see. Boom, the absolute value. So now we can see that the absolute value of x actually resembles more of what the square root of x squared should look like. And so now if we think about our function, we have the square root of x minus 1, and that's being squared. You're going to get an absolute value function at 1. So now, instead of doing a chain rule because we have a composition here, we have to think about the absolute value function for a moment. When we think about this absolute value function, we know that because there's a minus x, that the absolute value mother function, the common function, would not be right there. It would be shifted over to the right 1. So we're going to put a 1 right here, and this is what we got. Okay, so if we were to take the derivative of this function, we would get two different answers. Now, there's nothing that changes the steepness of this side or this side of the absolute value function. It just got moved over to the right. So you know that the slope of this side is 1, and you know that the slope of this side is -1. So if we have the derivative of the combination of these the composition, I should say, of these two functions, we actually get like a little piecewise function. We get -1 for all the x values that are between -infinity and 1, close parenthesis, or we could have used inequality signs, or +1 for all the x numbers that are more than 1, so from 0 to positive infinity. So I could have said x is less than 1, and for this one, x is greater than 1. Make sure you don't say equal to, because that is a point right there, and this function is not differentiable at points. No functions are differentiable at points. So that problem's done, but I kind of want to show you this as well. You could have thought about the problem a little differently. You could have thought about this x minus 1 and how it could have been a negative x minus 1, because the absolute value bars get rid of it. And so now if you took the derivative of each of these, we'll put primes next to it, this one would be 1 and this one would be -1. But it's important to note still that we're -1 for x is less than 1, and we're +1 for x is greater than 1. Now let's talk about this part of the FRQ. This k should actually, I should have written k of x. Okay, so it shouldn't just be k, just to be consistent, because I define j of x right here. And j of x is g, except it's only g for values that are greater than 1 or equal to 1. And why is that? Well, g equals, if I just look at the graph of g looks like this. Now, this function right here, g, does not have an inverse. Why? Because it doesn't pass the horizontal line test. So it doesn't have an inverse. So what I did here is I defined j to be g, but only from 1 to infinity. So now, from starting at 1, we have our function. This function does have an inverse because it does pass the horizontal line test. If a function passes the horizontal line test and the vertical test, that function is known to be 1-to-1. Only functions that are 1-to-1 have inverse functions. And so I know the way this is written is kind of confusing. It says k is the inverse to j, and then it says what j is. J is g, but only this side of g. I know that's kind of confusing. And then right here we have k inverse of 1. So we have, or not inverse, dang it, k prime of 1. But k is the inverse function. So because k is the inverse function, one way that we can find the answer is we can say that the derivative of k equals 1 over the derivative of j with k inside of it. That is the derivative of the inverse function formula. All right, so let's see if we can get all this information. First, what we're going to do is we're going to plug in 1 to the k. When I plug in 1 to the k, I get k of 1. I need to know the value of k of 1. Okay, so how do I find the value of k of 1? Well, let's think about this for a second. I like to use tables when I think about this. So if I was plugging in 1 to k, what would my k be? This also means that if I were to plug 1 into j, what would the x be? See, if I found the x value for when j is 1, then I also find the value of k for when x is 1, because they're inverses of each other. The x and the y's switch when you look at them. So I'm going to take the j function, which is the same as the g function, except for the domain is limited. So let's go, J is x minus 1 to the second power. And let's plug in 1 for the j and solve it. When I solve this, I square root both sides. You get plus or minus 1, x minus 1, and then I add 1 to both sides. So now I have x equals 1 plus or minus 1, and I get two answers, 1 plus 1, which is 2, and then 1 minus 1, which is 0. And when I consider these two numbers, I know that 0 is not in our domain, so it's not going to be part of the answer. Only 2 is. So that means 2 goes right here. If I plug 2 into j, I get 1. That means if I plug 1 into x for k, I get 2. So now I know what the value of this is. It is 2. So I'm going to write 2 right here and then rewrite everything over there. So we got 1 over j prime of 2. Now, do we know what j prime is? Well, in order to find j prime, I'm going to have to, again, think about what it looks like. So we have j prime of x equals, let's see. Oh, we found that earlier. We found g prime. So we know it's 2x minus 2. And so this equals 1 over 2 times 2 minus 2, which is 1/2. Boom. So that is k prime of 1. Our last question here is supposed to not say x equals 2. It's supposed to say x equals 1. Sorry about that if it did say 2 still. Now we're trying to find the tangent line equation. We know that the tangent line equation is y minus f of a. That's the y value at a. And then equals f prime of a. That's the slope at a. And then we have x minus a. But we're not using f, we're using k. So let's rewrite that. Let's say y minus k of 1, because that's where we're at. And then we have k prime of 1, and then we have x minus 1. So now we just have to substitute in what we know. What is k of 1? Well, we found that right here. If we plug in 1, we get 2. So it's y minus 2. K prime of 1, that's 1/2. That was the whole previous problem. Then we have x minus 1. I'm going to leave this as it is because that is a tangent line. I'm not going to solve it all the way. Now, if you were working with multiple choice type of a question, your answer would most likely have y alone. So if you want to practice that, you can go ahead and do that. But that's how you do this one.